Hi, I'm Denise Cooper from Royal Installation. So we're going to do a loop.
All right, Sparkies and future Sparkies, here's today's challenge question. If you change a main fuse rating, do you need to change the cable? If you upgrade a submain cable, does the earth need to be bigger? And if your fault current is too low, can your breaker fail to operate? These aren't trick questions. They're real-life problems electricians deal with all the time. And today, we're going to make all of this make sense. This is a foundational topic in the trade. Once you understand the relationship between the main supply cable, the protective device, and the earth conductor, you'll be miles ahead of most trainees, and even ahead of some lads who passed their AM2 10 years ago. Section 1. The real story behind faults and ads. Let's begin with what actually happens during a fault, because everything in BS 7671 is built around this. Imagine a live conductor touches earth, maybe a damaged cable, maybe a loose wire in a metal fitting. At that moment you get a fault current, which is usually much higher than the normal operating current. BS 7671 calls the protection system ADS, Automatic Disconnection of Supply. ADS is basically the rule that says, when something goes wrong, the supply must disconnect quickly enough to keep people safe and stop your cables from cooking themselves. Disconnection time basics. For most final circuits up to 230 volts, 0.4 seconds. For distribution circuits and submains, up to 5 seconds. For TT systems, times depend on RCD. Why? Because human shock tolerance and cable thermal limits are directly tied to time. The longer a fault lasts, the more dangerous it becomes. The key point for Sparkies is this. The fuse or breaker can only disconnect quickly if the fault current is high enough for its curve. If the fault current is too low, your breaker sits there doing nothing. This is especially common on long cable runs, old farms, TT systems, or properties with high ZE. Section 2. Understanding fault current and impedance. To know whether your breaker will disconnect within the required time, you must understand earth fault loop impedance, or ZS. Formula refresher. Z equals ZDI plus R1 plus R2, where ZE is the external impedance, DNO side. R1 is your live conductor resistance. R2 is your CPC resistance. The maximum allowed Zs is given in BS 7671 for each fuse, MCB type. If your Zs is too high, fault current is too low, fuse may not operate in time. For example, AB32 MCB typically needs around 160 amps to trip instantly in the magnetic region. If your fault current is only 80 amps, it won't hit that instantaneous curve, and the disconnection could take several seconds, which may fail the 0.4 second rule. So you can have a perfectly good cable, a perfectly good MCB, and still have a dangerous installation because the fault current isn't high enough. This is why the relationship between cable, breaker and earth is not optional. It's the core of safe electrical design. Section 3. Sizing the main supply cable properly. When you size a supply cable, whether it's a meter tail, a submain or a distribution circuit, you're not just looking at the load. You're designing for 3 conditions. 1. Current carrying capacity. IB less than or equal to in less than or equal to is. IB equals design current. In equals protective device rating, is equals cable capacity. 2. Voltage drop. Longer cables equals more voltage drop. BS7671 recommends a maximum of 3% for lighting and 5% for other circuits. 3. Fault withstand temperature. Your cable must withstand the fault current during the time it takes the device to operate. This is where the thermal constraints tables and Adiabatic come into play. Let's do a real example. Submain to a garage. Design current, IB, 32 amps. Length, 18 meters. Installation method, clipped direct. Protective device, 40 amps. Type BMCB, measured Zs. Target, under 1.15 ohms. If you choose 6mm cable, clipped direct, it's rated around 47 amps, so it passes current carrying. Voltage drop is low because it's a short run, but let's check the fault withstand. If the calculated fault current is 200 amps, that type BMCB will probably operate in well under 0.1 seconds, well within limits, so the cable is suitable. See? It's not just about load, it's about how the cable behaves under stress. Section 4. Protective devices, ratings, curves and braking capacity. Now let's talk about protective devices, the part students often overlook. 1. Device rating must suit the cable. In BS 7671 terms, IB less than or equal to IN less than or equal to IZ, meaning the fuse or breaker must protect the cable from overload. 2. Time current curves matter. Different devices react differently. Type B MCB, instant trip at 3 to 5 times in. Type C MCB, 5 to 10 times in. Type D MCB, 10 to 20 times in. BS 3036 fuses, slower, more heat. BS 88 fuses, very fast for high faults. So if your fault current is low, a C curve or D curve can fail the 0.4 seconds rule. 3. Braking capacity. This is how much fault current a device can safely interrupt. Examples: domestic MCB, 6 kiloamperes. Commercial boards, 10 kiloamperes. BS, 88 industrial fuses, 16 kiloamperes to 80 kiloamperes. If your PFC is 12 kiloamperes and your device is only 6 kiloamperes, that's a big fail and potentially dangerous. So with Sparkies, we choose devices to match both the cable and the fault levels at that location, not the other way round. Section 5. CPC and earth sizing with the Adiabatic equation. And now, the bit everyone fears. Sizing the earth using the Adiabatic equation. But honestly, once you understand it, it's one of the simplest formulas you'll ever use. Adiabatic equation. A equals the square root of I squared times T divided by K, where A equals minimum CSA of earth conductor, I equals earth fault current from ZS, T equals disconnection time from fuse or MCB graph, K equals material or insulation constant PVC copper equals 115. Let's walk through 2 different examples to get it clear. Example 1. Medium fault current, quick disconnection. Fault current, 650 amps. T, 0.1 seconds. K, 115. A equals the square root of 650 squared times 0.1 divided by 115. A equals the square root of 422,500 times 0.1 divided by 115. A equals the square root of 42,250 divided by 115. A equals 205.6 divided by 115, approximately 1.8 millimeters squared. So even though your line conductor might be 6 millimeters, your earth only needs to be 2.5 millimeters, because the fuse trips instantly. Example 2. Long run with low fault current, worst case. Fault current 120 amps. T, 0.4 seconds, final circuit. K, 115 equals the square root of 120 squared times 0.4 divided by 115. A equals the square root of 14,400 times 0.4 divided by 115. A equals the square root of 5,760 divided by 115. A equals 75.8 divided by 115, approximately 0.66 millimeters squared. Choose 1.0 millimeters squared minimum. See how the math works? Low fault current and slower tripping still produce small earth sizes. But remember, CPCS also have minimum sizes in BS 7671 for mechanical strength. So we never actually install a 0.66 millimeter conductor. Section 6, bringing it all together. So let's pull the whole thing into one complete picture. The cable must carry the running current and survive the fault. The breaker or fuse must protect the cable and disconnect fast enough. The earth conductor must carry the fault safely for the disconnection time. The fault current must be high enough for the device to actually operate. And ZE's installation method and braking capacity all tie the system together. Once you grasp these relationships, you're not just installing cables, you're designing safe electrical systems like a true professional. If this walkthrough helped you understand the full relationship between cables, fuses and earth conductors, drop a comment below. And you're free to ask questions too. Thanks for watching, Sparkies. Stay safe, stay smart, and keep those installations royale.